This video is about the additivity of Green's theorem. I'll describe exactly what that means in a little bit. We will use Green's theorem to come up with a line integral for area, and then I will prove Green's theorem for the special case of a horizontally and vertically simple region R. So just briefly, let's review. Here are both forms of Green's theorem. So let's say we have R, and R is a simply connected region. So that means every simple closed curve in R contains only points that are in R. If we have R, and R has a piecewise smooth boundary C, so in this picture, that curve there is C, and it's oriented counterclockwise, and our field F has components M and N have continuous first partial derivatives on an open interval, or excuse me, on an open region containing the region R and its boundary. So on a little, it looks like a neighborhood, but it's just a region that's slightly larger than R, so that it includes the boundary of R and R itself. M and N have continuous first partial derivatives there. Then both of these are true. These are two equivalent statements. The line integral of F over C is equal to this. So rather than evaluating the line integral, which requires writing F in terms of T, coming up with a piecewise smooth parameterization R of T, computing R prime, taking a dot product, and then integrating, we can say, let's not do that. Let's find the partial of n with respect to x and the partial of m with respect to y, and evaluate the double integral over R of that instead. This is often much easier than this. So we like this theorem because it allows us to evaluate this integral instead of this integral. Now, normal form, oops, there's a mistake here. This is not correct. In normal form, we've got this integral over here. This is the flux integral, and that tells you how much that field is crossing the curve C. That's equal to this double integral. And this integrand is the same as the divergence of F. So if you want to find the flux of the field through C, and you're counting this normal direction, that direction pointing outward as positive, then this is equal to the double integral of divergence. And then we said in the last couple of videos, one way that we can interpret this is that if F represents the velocity of some fluid, this is the flow or the circulation of that fluid around the curve C. Now, rather than finding the circulation around the curve C, what we can do is find the z component of the curl at each point, and that's giving us some measure of how much that fluid is turning about that point, multiplied by the area. And if you do that for all of the points in the region R, you're going to get exactly the same value as if you found the circulation on the outside. So somehow this curl, which we said informally is the measure of how much that fluid is swirling about a point, if we take all of those and we add them together and we multiply them by the area, that's actually giving us the same number as the circulation. So it's like somehow all of that swirling inside corresponds to what's happening on the outside with that circulation. So you can think of curl now as circulation per unit area in this context. Now, normal form, that gives us this right here. On the left-hand side, that represents the flux. So that's how much fluid is going out at a point. The left or right-hand side of the integral says that rather than doing that, rather than calculating how much fluid is crossing that curve at every point along the boundary, instead what you could do is find the divergence at on each of these little rectangles. And it turns out, because these little rectangles are adjacent to each other, what goes in or what goes out of this little rectangle goes into that one, and what goes out of this one goes into that one. So you're going to have a lot of cancellations. The only flux that's really going to count are the flux on the very outside. And again, often this is much easier to evaluate than this. So we like this theorem because it allows us to evaluate this simple integral instead of this one. And it also is, I think, very beautiful. It tells me that somehow this curl on the interior tells me about the circulation on the outside, or the divergence at every single location on the interior tells me about the flux through the outside. Okay, so let's get to this first topic, the additivity of Green's theorem. Additivity of Green's theorem addresses this question. You say, well, what if R, the region that we're interested in, is not simply connected? So let's say you've got a region R like this, and it's got this little piece missing. So now if I draw a simple closed curve that lies entirely in R, well, some of them are fine. Some of them only contain points in R, but I can draw at least one, actually infinitely many of them, that contain points that aren't in R. We're gonna have a problem. So actually it turns out there's a way we can get around that. If you have this problem, so Green's theorem doesn't apply, we can add a couple of little curves to our boundary, and then Green's theorem will apply. So basically what we'll do is we'll say, okay, let's add two curves here, and they're actually going to overlap. I'm going to draw them with a little space in between so that we can see them, but they truly should be on the same location. So the same set of points in the xy plane. So I want this curve to go this way. So I'm going like that. And then I want this curve to go in the opposite direction. So I'm going like that. And then when I put those two together, imagine they're lying on the same line segment here. Now I've got this. Now, if they're lying on the same line segment, this blue curve isn't allowed anymore because it crosses my boundary. And say, that's not cool, we can't do that. So now if I have that little line segment there, all of the simple closed curves that I draw in R will have to stay in R because I added this extra piece, extra two boundary curves. And notice that the line integral over this curve and the line integral over this curve, if they're lying in the same location, they're going to have exactly the same magnitude but opposite signs because one is going in one direction and the other one's going in the other direction. So instead of doing the line integral over C of f dotted with dr this way, I'm going to add two new pieces. I'll call this part, this little line segment, C sub 3, and I'll call this little line segment C sub 4. So we'll add a line integral over C sub 3, and we'll add a line integral over C sub 4. And that's actually, I'm going to write negative C sub 3. So those are opposite of each other. So those are going to cancel, and that's going to give me exactly the same value as this. Say, well, what does that mean? Well, with the introduction of those two little boundary curves to our region R, now I can apply Green's theorem to what's left. So the double integral over this region will be the double integral of the partial of n with respect to x minus the partial of m with respect to y. And I actually had a student last semester who said, okay, I get that, but how do I evaluate that if I've got two pieces now? Well, then you've got to, if you actually wanted to practically evaluate this, you would still have to come up with a way to describe this region and that region. So we would end up with a double integral over a larger region R. So I'm going to say this whole thing, this pink part, I'm going to call that R1. And R1 includes that little island that I'd like to exclude later. And then we're going to subtract R2. Now, it really doesn't make sense to subtract regions, but I hope that you understand what I'm trying to say. I'm just saying we'll take the double integral over the pink region, and then we'll subtract the double integral over R2, where R2 is that region right there. I'm going to put this in quotes because it doesn't really make sense to subtract regions. Okay, so then you'd say, what do you do in practice? You do this. You evaluate this for the larger region, and then you evaluate the same expression for the smaller region, and you subtract. So that's what we mean when we say that Green's theorem is additive. Basically, I can break this up into pieces and then evaluate or use Green's theorem for each of the pieces, provided that Green's theorem applies after the introduction of some little line segments here. So we had to add C3 and C4. And when we did, we were adding something that would essentially add 0 to the value of the line integral. So it doesn't affect the right-hand side of Green's theorem. And of course, you could add more little line segments if you wanted to. So you could do one piece over there, and then another piece over here. And that's what we mean when we say it's additive. Okay. Now there's also a special case of Green's theorem that gives us a line integral representing area. So we know from Green's theorem, the tangential form, that this is equal to this double integral under the conditions when Green's theorem applies. So provided those hold, these guys are equal to each other. Well, if this is equal to 1, then we just get area. So what this tells me is if I can come up with any field so F represents the field and it has components M and N, and the partial of N with respect to X minus the partial of M with respect to Y equals 1. Then the line integral over that field, and this is provided we've got a closed curve C, is the area of the region. Inside that piecewise smooth boundary C. And of course, all of the conditions of Green's theorem have to hold for this to work. There are actually lots of different functions that could give us this result. One pair of functions is given this way. Say we need the partial of n with respect to x to be 1/2, and we need the partial of m with respect to y to be -1/2. So we'll have 1/2 minus a -1/2, which is 1. If this is true, then the line integral over f will give me the area. Well, the simplest n and m that will give me that are these guys. If I need the partial of n with respect to x to be 1/2, if I take the antiderivative of that with respect to x, I get 1/2 x. If I need the partial of m with respect to y to be -1/2, if I take the antiderivative with respect to y, I could get m. So I have -1/2 y. And you should check, derivative of this with respect to x is 1/2, derivative of that with respect to y is -1/2. And then when we subtract these two partials, we have 1/2 minus -1/2, which is 1. So that means our double integral just becomes the double integral of 1, which is the area of R. Okay, well that means this line integral, the line integral over C of f dotted with dr, where f is the field with components m and n, it's -1/2 y and 1/2 x, provides the area of R. And this is if C is a closed curve with a piecewise smooth closed curve. Actually, let me check my words, make sure I'm saying this exactly correctly. I need C is a piecewise smooth boundary of the region R. It's oriented counterclockwise. R is simply connected. And M and N, they do have continuous first partials in the entire XY plane. So this will represent the area of R. Provided C is the piecewise smooth boundary of a simply connected region R. And C is also oriented counterclockwise. So it seemed like we were finding this very simple thing, very simple line integral that represents area, and we did, but we have to remember all of these requirements. Okay, so let's use this to find the area of a circle. And we want to find that area using a line integral. Well, of course, we already know the answer for this. This is a circle, or I guess I should say the area of the interior of x squared plus y squared equals 1 using a line integral. So it's just a circle of radius 1, centered at the origin. I can make my curve C go that way. Obviously, R is a simply connected region. Every simple closed curve in R lies in R, that's fine. C is oriented counterclockwise and is definitely piecewise smooth. So according to this, all I have to do is take the line integral over C of this function, and that is going to be the area of the region. Now, we know using geometry, formulas from geometry, this is going to be 1/2, or excuse me, not 1/2, it's pi r squared, and the radius is 1. So we know that the area is pi. We want to show that it's also equal to pi, or it's still equal to pi if we use this. This is just another way of calculating the same thing. Now, typically I wouldn't use this when I already know the answer, but when we're in this class and we're just practicing and learning, sometimes it's nice to have a problem that we already know the answer to see if we're doing everything correctly. Okay, so I want to evaluate this area as a line integral rather than a double integral. So I need a parameterization, a smooth parameterization of the curve C. Well, that's just the unit circle. So x can be represented by x of t and y can be represented by y of t. we'll trace that out as t goes from 0 to pi. Okay. So I've got my parameterization. And in order to evaluate this line integral, we need our field written in terms of t. So we need the field in terms of x of t and y of t. We need to compute r prime of t and dot those. And then we'll integrate from t equals a to t equals b, and a and b are these values. Okay, so we just need the field in terms of x and y and r prime and a dot product. Not too bad. For later. Okay. So my field was -1/2 y and 1/2 x, or those were the components of my field. And I want that in terms of t now. On the unit circle, y was equal to sine of t, and x is equal to cosine of t if I'm tracing that out in the counterclockwise direction. And r prime, that's the derivative with respect to t of this vector with components cosine of t and sine of t. Derivative of cosine is negative sine. Derivative of sine is cosine. And now I need to compute the dot product of those two guys. This times this is a negative times a negative, so that's positive. Sine times sine is sine squared. Then we're adding this times this, 1/2 times cosine squared. And factor out a 1/2. And we get that beautiful trig identity, so it's gone, we get a 1. So I have a 1/2 there. So what did we do? We found the field in terms of t by substituting x of t and y of t. We computed r prime, and then we computed the dot product. And now we just integrate that dot product according to our earlier results. The area of the region R is 1/2 of the, or excuse me, is the integral from 0 to 2 pi of 1/2 with respect to t. So we get 1/2 t, we evaluate at 0, we evaluate at 2 pi, and we subtract. And 1/2 of 2 pi is pi. So we just substitute into the line integral and evaluate. So this is nice. So this will allow us to find an area using a line integral, and it might be useful in other cases. There might be other times if I don't actually want to compute the area, but I need to write the area in a different form. I can use this fact. Now, an alternate notation for this is this. We've got the integral, the line integral over c of f dotted with dr, and f has components -1/2 times y and 1/2 times x, and dr, we know that's x prime, y prime dt. When I multiply those together, oops, I don't really need that anymore. T is going to go from A to B. I'll have -1/2 y times x prime of t dt plus 1/2 x times y prime of t dt. And this is dx by definition, that is dy. So in differential form, oops, using a scratch paper from a different video, we can pull out the 1/2, and we can write it this way. It's the 1/2 of the integral over C of x dy minus y dx. That represents the area of R. Now, I don't tend to use that. I prefer this dot product notation, but it's equivalent. So if you like that better, you can use this. Again, what did we do? We said, if this is our field F, if I take the partials with respect to x and y, as I'm supposed to for Green's theorem, I get an integrand of 1. So the line integral over this field is the same as the area of the region. The last thing we'll do in this video is a proof of Green's theorem. And this is just for the special case when the region R is both horizontally simple and vertically simple. Now, a horizontally or a vertically simple region is a region like this. It can be described this way with rectangles that are oriented vertically, hence the name vertically simple. Y goes from a function to a function, while x goes from a constant to a constant. A region's horizontally simple if we can draw our rectangles this way, and the whole time x goes from a function to a function, and y goes from a constant to a constant. Green's theorem holds when our region is not both vertically simple and horizontally simple, but it's easiest to prove in that case. So I'm just going to prove it in that very special case. So let's say this is our region R. I hope I drew something that was horizontally simple and vertically simple. I think I did. Shouldn't have that weird little divot in it. I don't know. I don't even know if that divot's the right word. It's okay. All right. No, I didn't draw something that was horizontal or vertically simple. Let me draw it again. I think that'll work. Okay. So at x equals a, we're over here. And x equals b, we're over here. And if this is vertically simple, I can draw my rectangles this way. So y goes from a function to a function, and x goes from a constant to a constant. This bottom function is a function that I'm going to label f sub 1 of x. And then the top function I will label y equals f sub 2 of x. So x goes from a to b, and y goes from f sub 1 to f sub 2. The whole approach to this is that we're going to look at m and n, and we're going to look at line integrals over the curve, and then also look at double integrals over the region for each of those functions. And then we're going to be able to add those two pieces together to get our result for Green's theorem. Okay, so that's the plan. So let's look at the line integral over m of c. And this yellow curve, I'm going to represent by C1. And this blue curve, I'll call C2. So C is the union of C1 and C2. That's one way of looking at C. So the line integral over C of m is the same as the line integral of m over C1. So we're going to take the function m and integrate over that curve, and then we'll take the function m and we'll integrate over the other curve. Well, since we're integrating with respect to x, I can write m in terms of x and y. If I'm on C1, y is equal to f1 of x, and x goes from a to b. So m is usually a function of x and y, but since I'm on C1, I want to write it as a function of x and y is a function of x, which is f sub 1 of x. And then when I'm on C2, remember we're going in this direction. We want this curve oriented counterclockwise. When I'm on C2, x does not go from a to b. This time x goes from b to a. But it's very similar. X is still x, but this time when I'm on C2, I'm on this blue curve, y is equal to f sub 2 of x. Well, remember from Calculus 1 that if you want to flip these, you can, as long as you change that sign to a negative. I want to do that because I want these to both be integrals from a to b. So the integral from a to b of m of x and f sub 1 of x minus the integral from a to b of m and x and f sub 2 of x dx right there. So the line integral over c of m ends up being this. And I've got the same bounds, so I can write that as a single integral. That's m of x and f sub 1 minus m of x and f sub 2 of x. Okay, so that's a line integral. Now I could also look at the double integral over r of the partial of m with respect to y. And if you're saying, why are you integrating the partial of m with respect to y? It's because that's the term that we see in Green's theorem. I want to show that this is related to this. Well, if we have a vertically simple region, this region R can be described this way. X goes from a to b, and y goes from the bottom function to the top function. And this is the partial, the integrand is the partial with respect to y of m. Now, if we're integrating, evaluating a double integral, we always start on the inside first. Well, the antiderivative of the partial of m with respect to y is m of xy. And then we evaluate from f sub 1 of x to f sub 2 of x, and we subtract. And so we have m of f sub 2 of x, m of x and f sub 2, and m of x and f sub 1. Now I want you to look at it. Look at the similarity between this and this. They're not identical, but they're very close. Here I've got f1 and f2, and I'm subtracting m at f1. I'm doing m at f1 minus m at f2. Here it's just the other way around. So what does that mean? That means that the line integral over c of m is equal to the, negative double integral of the partial of m with respect to y over r. Okay, so that was that piece. And now I want to, remember what Green's theorem says. This is what we're trying to prove. Trying to prove that the line integral over c of f dotted with dr, which is the same as m dx plus n dy over c. We're trying to show that that is the same as this double integral. And so far, what I've found is that the line integral of m with respect to x is equal to the double integral over r of the negative partial of m with respect to y. So now what I'd like to show next is that the line integral over c of n dy is equal to this piece. Once I can show that's true, then I can just put them together. Now all this hinges on the fact that this is equal to that, and we did that in our very first video when we showed that this line integral can be written in differential form. So when we first started talking about line integrals, we proved that. So go back and watch that video if you don't remember why that is true. Okay, so let's do this piece. Now I want to show that the line integral of this piece is equal to the double integral of that piece. In order to do that, I need to look at this curve C, but I need to look at it differently. Rather than looking at it as a vertically simple region, I need to remember that it's also horizontally simple. I feel like I could almost just sketch it right here, but it's unfortunately the reflection. That's okay. Trying to draw the same thing. X equals A, we were here. X equals B, we were here. Now we're saying, let's look at it from a different perspective. Let's say that Y starts here at C and Y ends here at D. And let's look at the curve on the left. So that's X is a function of Y on one side. And then I've got a curve on the right. X is a function of Y on the other side. So Y goes from C to D. And X starts at this function on the left. I'll call that G sub 1 of Y. And I'll call that C1. Well, actually, I've already used C1 and C2 for something. Let's call these C3 and C4. C is equal to C3 union C4. That's the same C from before. And C3 is just that side. Oops. Given by X equals this function G of Y. And C4 is the X on the right. So X is equal to that function, G of Y. Okay. All right, so now let's look at the line integral over n, with respect to y. Well, that's going to be the line integral of n with multiplied by dy over C3 plus the line integral over C4. And on C3, y goes from C to D. But the whole time, x is equal to g sub 1 of y. And then over here, actually we're going this way. Ooh, that line integral over C3, actually x is, or y is going from D to C because we're going this way, because we're oriented in the counterclockwise direction. Sorry about that. Keep doing the wrong thing. We start at D and we go to C because we're going from up here down to here. Okay. Now on this curve, we still have n as a function of y, but on this curve, x is given by g sub 2 of y. And we're integrating with respect to y. But on this curve, y does go from C to D. Well, we would like them both to go from C to D, so we have to multiply this one by -1. So we can flip that. And now we've got the integral from C to D of this one, which is positive, minus that one. You see where it's going? I hope you do. Okay, we've got that right there. The claim is that that's the same as the double integral over R of the partial of n with respect to x. And I think you can see it because we have a horizontally simple region. Y goes from a constant to a constant, C to D. X goes from the left function to the right function. So it's g sub 1 of y to g sub 2 of y. And then we've got the partial of n with respect to x here. And then we start on the inside and we work our way out. The antiderivative of the partial of n with respect to x is n. And then you replace x with g sub 1 of y, and you replace x with g sub 2 of y, and you subtract. You see it? It's exactly the same as what we got up there. So the line integral over C of m dx plus n dy, which is the same as the line integral over C of f dotted with dr, is equal to the double integral of the negative partial of m with respect to y plus the double integral of the positive partial of n with respect to x. And since we have exactly the same region of integration, we can write it this way. Put the positive term first. So that's Green's theorem. I hope you can see, even if you didn't do the calculations, I hope you start to notice the pattern. When you're doing the line integral over C of n, because C can be described this way, x can be replaced by a function of y and a function of y, we end up with this. And then when you look at that and then you compare it to this, I think it's almost obvious exactly what's going to happen. The antiderivative of something with respect to x is just going to be that original thing. And then it's almost like the delta x and the partial of the x cancel. They don't cancel, but it's almost like that's what happens. And you end up with this n dy here, just like you had an n dy up there. But all this is more technical and more valid than that intuition that are like, hey, look, it looks like the dx's cancel and you've got this change in n times dy. And that's a change in n times dy. Yeah, so that's how we prove Green's theorem in that very special case.